Welcome back to The Explainer. I am honestly so thrilled to share today's topic with you because we're going to look at a genuinely revolutionary way that machines are learning to process language. It's called combinatory categorical grammar, or CCG for short. Think about it for a second. How do you actually teach a machine to untangle the messy, chaotic web of human language? Computers, they're intensely logical, right? But human language, well, it's totally not. It's packed with weird exceptions, implied words, crazy phrasing. For decades, traditional parsing models have basically banged their heads against the wall trying to solve this massive puzzle. Okay, let's dive into this. We've got a clear roadmap today to make sense of this incredibly dense computer science topic. We'll hit shifting grammar to words, categories in the lexicon, the rules of combination, handling advanced sentences, super tagging to solve ambiguity, and finally, parsing with A-star search. So, step 1. Shifting grammar to words. Let's look at the paradigm shift. To really get CCG, you've got to understand the core problem with those early parsing models. In traditional phrase structure grammar, the system relies on this massive, heavy rulebook of grammar rules while treating the words themselves as, well, simple, dumb building blocks. CCG completely flips this on its head. It takes all that grammatical complexity and just crams it directly into the vocabulary itself. We call this lexicalization. So instead of a giant overarching rule book, you're left with just a tiny handful of basic rules, while the words themselves become highly complex and, essentially, smart. Okay, so how exactly do we make words smart? That brings us to section 2, categories and the lexicon. Let's check out the building blocks. CCG uses something called slash notation. Now, I know it looks a bit like algebra, but let's just translate this into conversational math using a Lego block analogy. Think of these functions as hungry puzzle pieces. An x/y is simply a Lego block that is hungry for a y block to its right. If it finds it, boom, they snap together to create an x. An x /y, exact same thing, but it's looking to its left for that y block. Let's look at some actual words in our lexicon to see this in action. Simple words like flight or Miami, those are atomic categories, just standard nouns or noun phrases. They're your basic, simple Lego blocks. But look at a transitive verb like cancel. Its category is super complex. It's actively looking for a noun phrase to its right, and if it finds one, that whole block actually transforms into a new function that starts hunting for another noun phrase to its left. Once it gets that, it ultimately yields a complete sentence, or an S. The word itself carries the exact blueprint of how it needs to fit into a sentence. Absolutely brilliant. Now that we've got our smart, hungry Lego blocks ready to go, let's move to section 3, the rules of combination, and start putting it together. Because we pushed literally all the complexity into the words themselves, the actual rules for combining them are incredibly basic. Basically, there are just 2 fundamental rules dictating how our slash notation Lego pieces snap together. You have forward function application, where the function eats the argument to its right, and backward function application, where it eats the argument to its left. That's pretty much the whole shebang. Let's see how this builds a full sentence step by step. We'll start with our raw words, United serves Miami. Next, we assign their categories from the lexicon. United and Miami are your simple noun phrases, but serves is our hungry verb. First, through forward application, serves grabs Miami to its right. Then, through backward application, that resulting block grabs United to its left. In CCG, you'll see these derivations growing downward from the words, kind of like an inverted tree, snapping together until we get a single complete sentence category right at the very bottom. That works beautifully for simple sentences, but human sentences are messy, right? We coordinate and combine things in weird ways that totally break traditional rules. So let's jump into section 4, handling advanced sentences. This is where we see CCG's superpowers. To handle all those messy sentences, CCG brings in 2 advanced operations, type raising and composition. Essentially, type raising takes a simple, boring category, like just a basic noun, and elevates it into an active function. It literally turns the prey into the predator. And composition allows those adjacent functions to combine directly with one another. Here is why this is such a real game changer. Look at the sentence, we flew Icelandair to Geneva and Swissair to London. Now, in traditional syntax, the phrase Icelandair to Geneva is not a normal constituent. It's a messy fragment. Traditional grammar engines just completely break down trying to map this out. But CCG, it handles it elegantly. By using backward type raising and function composition, CCG actually turns Icelandair into a function that merges directly with to Geneva, perfectly pairing these non-constituents before combining them with and. It totally proves its superiority over older models by matching how humans actually speak. So the theory is brilliant, for sure. But let's shift from theory to practice in Section 5, super tagging to solve ambiguity, and look at the machine learning reality. How does a computer actually guess all these complex/categories out in the real world? Because out in the wild, we run into a massive wall of ambiguity. Take a sentence like, United diverted the flight to Reno. Does to Reno modify the word flight, like a flight destined for Reno? Or does it modify the verb diverted, meaning the act of diversion happened toward Reno? In the primary CCG tree bank, which is known as CCG bank, there are over 400 practical lexical categories. A simple word like to could have multiple completely different mathematical functions depending on the context. If a parser just guesses blindly, it is going to drown in millions of wrong combinations. No way it works. We solve this massive wall of ambiguity with super tagging. Super tagging uses machine learning, specifically neural sequence models or conditional random fields, to look at the sentence context and generate a probability matrix for each word. Instead of giving the parser every possible tag, it assigns probabilities. For example, for the word serves, the model might be 80% confident it's a transitive verb and only, say, 10% confident it's a standard noun. This probabilistic filtering avoids a massive explosion of wrong guesses before the actual grammatical parsing even begins. Which brings us right to our final section, parsing with A-star search, or the search for the best path. We have our super tags and their probabilities, right? But we still need a way of finding the best path through all that math to uncover the single perfect sentence structure. So how does the parser algorithm actually sift through thousands of possible grammatical combinations efficiently? Because if it tries to build every possible sentence tree at once, the computer will literally run out of memory. The answer is a really clever heuristic search algorithm called A-star. A-star works by calculating a cost function for every partial phrase it builds. It adds the inside cost, which is the exact mathematical cost of the phrase it has built so far, to an outside cost, which is a highly optimistic guess of what the rest of the sentence will cost based on our super tags. By converting our probabilities into negative log costs, the parser simply treats parsing like a map routing problem. It always explores the least cost, most probable Lego block combinations first, pausing any path that starts to look mathematically expensive. The crucial point here is that unlike older bottom-up approaches that meticulously build every possible partial phrase, creating thousands of useless zombie constituents, A-star successfully terminates the exact moment a complete optimal sentence derivation rises to the top of its agenda. No wasted time, no zombie constituents clogging up the memory. It's incredibly efficient. And this brings us to why all of this actually matters for the future of AI. By shifting the complexity to the words themselves, CCG allows the algorithm to parse a sentence in a highly unique way, a left-to-right, word-by-word derivation. It doesn't need to wait for the end of the sentence to start understanding how the beginning fits together. It processes incrementally. And this psycholinguistic relevance is what makes CCG so endlessly fascinating to me. When you or I read a book, we don't hold a massive grammatical rulebook in our heads and wait for the period to arrive. We understand the rich, hungry functions of the words the moment we read them, anticipating what comes next. So I'll leave you with this. By processing language left to right, word by word, have we finally taught computers to read exactly like humans do?